Global Geodetic Observing System, how this organization is incorporated into all the other Earth observing programs of the other scientific disciplines. And after all the political stuff, we had a closer look on the joint determination of different geodetic quantities like the Earth rotation, the gravity field, the TRF, the satellite orbit parameters, and we learned that all of them are somehow correlated with each other. So in order to obtain reliable estimates, we have to combine the different techniques to take advantage of the different strength. And afterwards, we had this excursus into the different tide systems, where we compared the tide free, the zero tide, the mean tide, and its instantaneous tide system. And roughly speaking, the instantaneous tide system is the real world, and then you can remove all the time variable part, and then the treatment of the permanent tide. And finally, you end up at the tide free system, which would be the tide system when sun and moon do not exist and no external gravitational accelerations force the Earth body to deform. And afterwards, we somehow went over to today's topic, the combination of the geodetic techniques on ground and for the estimation of the TRF. And there we had already a kind of look on the local ties, the terrestrial difference vectors on ground, which are surveyed or which are obtained by surveying campaigns. And in contrast to this, we also faced the collocation in space, where the connection of the reference points is not at the ground side, but at the satellite platform side. And this will be the topic of today, a little bit. So how can we combine the reference frames how can we combine the geodetic techniques in order to estimate or determine a reference frame, so the station coordinates on ground. First of all, I want to go back to this kind of complex slide we had during the last lecture, where we have the gravity variation and surface deformation on the one hand side, the Earth rotation on the other hand side, and then the impact of the different geophysical effects on these quantities which can be measured by geodesy or geodetic space techniques. And some of you asked me to provide somehow the magnitudes of these effects, and I here face to the magnitudes of the surface deformations, because they are somehow good to understand in the units. So we have, for example, the atmospheric loading, which influences the surface deformation at the millimeter level. Ocean loading is causing millimeter to centimeters. We have the earth tides, which are causing centimeter to decimeter. So the usual variation in Munich is, for example, 24 centimeters in height due to the earth tides. And then we have a couple of other effects, and you can see that the majority of them somehow causes deformations at the millimeter up to the centimeter level. But we also have phenomena like earthquakes, which somehow cause deformations up to meter level. And this is exactly what we want to talk today about, because we talk today about the TRF, the terrestrial reference frames, so the station coordinates, and we also will face some of the phenomena again and see how they, or to what extent they are impacting point positions fixed to the Earth's crust. So this will be today's topic, and the TRF can be, the discussion or the lecture of the TRF can be started with such a citation by Kovalevsky et al. In 1989, so quite an old one, but this is more or less also the introduction to their book for reference systems. And they state that the Earth, its environment, and the celestial bodies in the universe are not static. They move, rotate, and undergo deformations. That's for sure clear, obvious to everybody. And the study of their kinematics and the dynamics that are behind is one of the major tasks of geodesy, geophysics, and astronomy. And this leads us to the point what kind of change or what kind of geophysical phenomena cause these changes. We have, for example, lithospheric plate motion, so you all know the plate tectonic motions, Earth and oceanic tides. We have loading effect, polar motion, Earth rotation, dynamical behavior of the Earth-Moon system, tides caused by other planets. So you see, we somehow already faced all these kind of phenomena. And in order to describe this, the next prominent statement in this book, in the preface, is that motions and positions are not absolute concepts and can be described only with respect to some reference. And that's exactly the introduction to the topic. We need a reference system which is long-term, stable, and precise in order to describe motions with respect to this reference system. We learned, I think, in the very first lecture that the GGOS goals are somehow 1 millimeter for the positions and 0.1 millimeter per year for the stability or for the motions. And this high accuracy, for example, is required in order to describe, for example, the sea level change, which is much smaller with respect to some long-term stable reference. Examples for such motions are, for example, the observation of the global sea level rise, observation of post-glacial uplift, so the deformation or the relaxation movement of the crust in the Scandinavian region, for example, due to the loss of the ice mass on top, or, for example, observation of seismic and post-seismic deformations in especially the South American region or the Japanese region, where the two largest earthquakes in the last 20 years happened. So Chile and Japan, for example. And for sure, we need reference frame for the cadastral measurements. Quite prominent example is this bridge building somewhere at the German-Swiss border, which was also in the news. So they started to build a bridge from the German side and from the Swiss side, and in the middle they recognized, quite before the middle, that they do not agree because Germany referred to another reference system than the Swiss colleagues, and therefore somehow they get this frequency. In the middle, which was about 54 centimeter in the height. So this was because the German height system refers to the Amsterdam height gauge and the Swiss one to the NIS height gauge. So, and they are not uniform, they refer to different heights, and that's why there was this problem. Another example is georeferencing of diverse environmental related data sets. You all know the geoinformation system, the GIS systems, and that's quite obvious that the georeferencing, so the relation of these different, let's say, data sets with respect to the Earth or with respect to some reference must be achieved in one reference, which is common to all of these different layers, and that's why you need a reference system in order to, for example, rely or relate the boundaries to the elevation or whatever. Yeah? So in order to georeference the different data sets, you have to have one common stable reference system for all these different data sets. And because we always talk about reference systems and frames, there is a really important difference. So the reference comprises a reference system and its realization, the reference frame. And there's this is really important now, so please have a look now, because the reference system is the conceptual definition of a basic principle which must be obeyed. So it's the theoretical definition of what you want to do, how you want to realize the reference system. Mostly this concept is an ideal reference system, since its definition does not imply to actually construct the system, which means in fact it's a theoretical system which might, for example, not be observable at all. Yeah? It will become clear in a couple of slides. Examples for such reference systems are the International Celestial Reference System, which we already faced in the last lecture, because that system somehow describes the inertial frame in which the Earth is moving and rotating. And for example, the ITRS, the International Terrestrial System, which is a crust-fixed system and co-rotates with the Earth. So within this system, you can describe all the different changes or deformations or geophysical phenomena which happen within the Earth system. And on the left-hand side, we have the definition, and the realization of the definition is the so-called frame. That's why we have then the terrestrial system reference system, and vice versa, the realization, the reference frames. And the reference frame materializes the reference systems in order to quantitatively describe positions and motions on the Earth. So the frame and the system is the theoretical definition, whereas the frame is really comprises the coordinates, so the numbers of the points, or some numerical values of the points or the celestial bodies. And the actual construction for sure implies a choice of a physical structure whose motions in the ideal reference system can be described by physical theories. For example, we have the solar system and we have the planets, which follow some physical laws or celestial mechanics. So that are the physical or the physical background. And the realization is based on a set of chosen parameters. Such a choice is not unique, and there remain always some degree of imperfection and arbitrariness. What does this mean? That means, for example, that as we will see it afterwards, the reference frames rely on some physical constants, fundamental constants, like the SE units or the speed of light value, which are for sure not perfect, but are the so-called defining constants. So based on these constants, then theory can be evolved. So that's somehow this kind of chosen set of parameters. And that's why these frames, or a frame is called a conventional reference frame, because for sure it relies on conventions. In the geodesy, or in geodesy we have the IRS conventions, Convention of the International Earth Rotation Reference System Service, which explicitly defines these fundamental values. And then for in case of the International Celestial Reference System, we have the ICRF, which is the Celestial Reference Frame, and the ITRF. And the ITRF is the topic of today's lecture, the International Terrestrial Reference Frame. How does it look like to come from a system to a frame? There are 5 major steps needed to do so. So first of all, you have to set a theoretical concept, which means that you have to describe or think about what you want, what your reference system should look like. For example, you want to have a reference system for the solar systems, or for the inertial system, or for the Earth body, for example. So after the theoretical concept, where you also, for example, define it should be a 3-dimensional reference system, you have to choose a physical structure. That means that the identification of physical bodies that support the definition, and together with the concept, both constitute the reference system. And here an example is given for the solar system. The physical structure is, for example, that the solar system is the physical structure to which one can apply the concept of this ideal reference. Basically, this means the ICRS is the celestial reference system for the solar system, and within the solar system you have this, and this kind of planets, kind of celestial motions or celestial mechanics, the Keplerian laws and so on, which base this structure on some physical laws. Afterwards, you have to model the structure. So you have to assign numbers to the parameters which describe the system. For example, the mass of the planets, mass of the sun, an AU, an astronomical union, or the speed of light, and so on. So you have to define some kind of physical constants in order to describe the system. The values, as we heard it before, are chosen necessarily and will have some arbitrariness. And therefore, the modeling representing the system is the so-called conventional reference system. And afterwards, it's directly moving on to the realization. So the 4th step is the realization, applying the model described by the conventional reference system. The coordinates of a certain number of points are determined from observations together with their variation of time. And this is exactly what we do in geodesy. We use spaced geodetic observations like GNSS, SLR, VLBI, DORIS, and so on, in order to determine point positions on the Earth crust, or we use VLBI observations in order to determine the coordinates of the extragalactic quasars, so in the ICRF. And this set of markers realize realize the so-called then conventional reference frame. So system is the definition, frame is really the realization, so the numbers of some points you determine or you relate to the observations. And the last step is then the extension and densification. If, for example, the system, or let's say, you estimate the coordinates in a least squares adjustment, and if you estimate too much coordinates, it can be too costly in terms of computational efforts. That's why you, for example, estimate only a subset of coordinates, which means, in fact, for example, in the case of the IQRF, we only estimate 1,500 globally distributed station coordinates within this ITF realization. And then for sure you have the Japanese region, or where you have at least 20,000 GNSS antennas, so that is a really dense network there. And this network is then the so-called densification of the IQRF. So the regional densification of the global reference frame, in order to avoid that only some institutions have to estimate all the coordinates, because that's becoming really computationally costful to do all the computations, but we will come back to this later and provide some numbers. Example is, I said, for the Japanese region, but also the SIRGAS reference system is a densification of the South American and Caribbean region. Okay, so any questions so far to these 5 steps? No? So it's really obvious and straightforward, this definition. And now we have a closer look on the IHLS, since this is the major topic, because we need this in order to quantify all the geophysical phenomena that we have within the Earth system. So the geocentric terrestrial reference system is defined to be a trihedron whose basic vectors span a 3-dimensional, orthogonal, and right-handed Euclidean vector space. In fact, it means that you have a 3-dimensional perpendicular axis to each other and right-handed Euclidean vector space. Right-hand means that with the right-hand rule you can define the three axes in x, y, and z. The system contains geocentric space-time coordinates, which means, in fact, that the time system of this reference frame is geocentric, which means that you realize the time, for example, by placing a maser or an atomic clock in the geocenter of the Earth. And there you see that it's already a kind of, how to say, it's obvious that you cannot place the atomic clock in the geocenter, so there's a discrepancy between the system and the realization, so the theoretical definition and the realization, because theoretically they define that the time should be geocentric, but the geocentric time is not accessible for us, for sure. We cannot access the geocenter, we cannot go there and place an atomic clock there. That's why there will be always a discrepancy between the realized time, because we place our atomic clocks usually on the Earth's crust, and then with the so-called UTC, for example, Universal Time Coordinate, so one global time system, and this for sure differs from the system-defined geocentric time. It co-rotates with the Earth and is related to the GCRS, so the geocentric celestial reference system, through spatial rotations using the Earth orientation parameters. So you have the GTRS, which is the geocentric terrestrial reference system. You have the GCRS, which is the inertial system, but the origin is also located at the geocenter. So you have only rotations between these two systems. And that was formulated in an IOGG resolution. IOGG, International Union of Geodesy and Geophysics. So the umbrella or the roof entity on top of the IAG and GDOS in 2007. So that's the drawing. We have the GCRS on the one hand side, which comprises 2-dimensional coordinates of quasars, extragalactic quasars. We have the GTRS on the other side, where you see the different points and some motions of these points, and in between we have the Earth orientation parameters, which consist of precision of nutation, universal time length of day, and the terrestrial pole coordinate. We will have a closer look on the EOP in the next lecture, I think. So, not too much information on this here, but simply they describe the transformation or the relation between these two reference systems. Okay, and within the above mentioned IOGG resolution, the ITRS is already defined as a specific GTRS with an orientation maintained by the Bureau International de l'Eure, BIH, and this means that the ITRS origin coincides with the geocenter, which is the center of mass of the Earth, and not only of the solid Earth, but also of the fluid the solid Earth and the fluid envelope. Yeah? So you have to take the whole Earth system into account, and the barycenter of this system is then the geocenter. So the center of mass of the Earth and the fluid envelope, which means including the oceans and the atmosphere at any epoch. So this is a really stable point in time. That is always the origin. Coordinates are 0, 0, 0. The orientation is an equatorial orientation, which means that x and y, or at least two of these axes, lie in the equatorial plane. So the plane spanned or realized by the equator. And the orientation and the third axis is then, since it is a three-dimensional orthogonal system, perpendicular to these, which coincides roughly with the Earth's rotation axis. And the epoch or the orientation is initially given by the BIH at the epoch 1984.0, which defines the x-axis going through the Greenwich meridian. This means that this point, this axis here, and the Pierce point of the x-axis on the Earth's crust is longitude equal to 0, which means the meridian, which is also going then through Greenwich. It's slightly wrong here. This axis should be 0.2. And the scale, finally, because this is the last quantity we have to know in order to have the system defined, is the scale, which is consistent to the TCG, so the geocentric time, as we said before, and the unit is the SE meter. So these statements give us the theoretical definition of the system. So this is more or less the, as we had it before, the physical choice and the modeling of the structure now to a certain point. Yeah?
Is the word co-rotates with the Earth a little bit different?
What do you mean?
In the definition,
Yeah.
it co-rotates with the Earth.
Yeah.
So what does this mean here? Because at the surface, or because there is always a custom moment difference to the linear.
That's true, but co-rotates with the Earth means that since you have an orientation given, which means that the x-axis points through the Greenwich meridian, and the Earth is rotating around itself in one day, yeah. So also the Greenwich meridian is rotating. So that co-rotating means that the reference system rotates with the Earth. So on one day around itself, and 365 days around the Sun, and so on. And this diurnal rotation, as you see, is, for example, exactly this universal time length of day. So this is a transformation already needed in order to go from an Earth-fixed reference frame, which really rotates with the Earth on a daily and an annual and semi-annual basis, to the GCRS. All motions, like, for example, for sure, also the Greenwich meridian, the realization of the Greenwich meridian is affected by plate tectonics and deformations and whatever. This for sure enters into this equation, while this is also a theoretical thing, let's say. It cannot be realized perfectly, but in a mean sense, the x-axis should point through the Greenwich meridian, despite all the small effects, let's say, but the main effect of the diurnal rotation is is not included in the terrestrial part. That means co-rotating. Okay, that's only a point view here. We have at any epoch means the origin always coincides with the center of mass. We have a time-independent definition of the scale, which should be always the TCG time coordinates, and the unit length of the meter is e-meter, which is also stable in time. But here we have a epoch given, so we have to think about, okay, how is the temporal evolution of this orientation, of the definition, and this is shown here. The system's time evolution of the orientation is ensured by using a non-net rotation condition with respect to the horizontal tectonic motions over the whole Earth. The ITRS is defined, realized, and promoted by the IRS. What does this mean now in non-net rotation condition? You have to think, you have the Earth body, and then you have globally distributed stations, yeah, all over the Earth, let's say 1,500, and you measure the motions of all these stations. Yeah, and there's one, you can distinguish the motions of these stations into two parts. You station individual motions and station motions which are equal to the common network. For example, the diurnal rotation. So the whole network is rotating one day around itself. Yeah? And this is minimized by subtracting the common part out of it and constraining this to zero. So the stations are not allowed to move on one day around itself. Yeah? That's why it's co-rotating with the Earth, because the reference system is not allowed to not perform this daily motion. And that means then that all the rotation or the part of the station motions which is common to all the stations, so more or less the network motion, is constrained to be zero. This means there's no net rotation condition, so no rotations, no horizontal motions are allowed at all for the common part of the network. Yeah? And that constraint ensures that the reference system is co-rotating with the Earth, since no common rotations are allowed. Huh? Is that clear for everybody? What no net rotation means? So it's a mathematical constraint, it's nothing physical, it's pure based on mathematics. You have a network motion and you subtract everything which is common to all stations and set it to zero. The conventional realization of this ITRS is the so-called ITRF. And Kowalewski and Müller already defined this, that the ITRS is realized through three-dimensional coordinates and velocities of points fixed to the Earth crust. And how can these points look like? Well, on the one hand side, you have monument points like markers. So this is somehow a geodetic reference point of the Bavarian Kadaster. And you see, if you place your GNSS or your handheld here, you have the exact coordinates of these points given below. For the space geodetic technique, we have another group of reference point, the so-called reference point of the intersection lines and reference points. For a GNSS antenna, for example, it's the phase center, the electric phase center of the GNSS antenna, which is the reference point. For a telescope, VLBI or SLR, it's the intersection of the rotation axis. So this gives you the reference point here. And what we get, or what we obtain from the space geodetic observations, are exactly the coordinates of these points, and if we have geodetic pillars and place a GNSS antenna here, we have the coordinates of these points as the realization of the ITRF, the ITRS. So this is the ITRF. The markers or anyhow reference points at the Earth's crust. And for sure, these reference points undergo changes, deformations, or whatever. They are affected, for example, by geophysical phenomena, for example, post-seismic or post-glacial relaxation motions. We have instrumental phenomena like gravitational deformation of radio antennas, phase center variations due to electric fluctuations or whatever, or anthropogenic phenomena, for example, due to groundwater withdrawal in the South Californian region. I will show an example of this later on. But that are somehow points, or that are effects which cause the reference points to move in time. To keep the ITS realization up to date as possible, the ITS is computed usually every 3 to 5 years by 3 different combination centers that are the so-called ITRS combination centers. And there's one in Paris, in France, which is the IGN. Then there's the DGFI in Munich, so part of the Technical University, and the JPL, the Jet Propulsion Laboratory of NASA in Pasadena, California. And the most recent solution of the ITRF is the ITF 2014. DGFI, we compute the DTRF 2014, which is the same reference system that is released by the ITRS Center. So every 3 to 5 years we have to do this computation. It usually takes 1 year to achieve solutions, or to get solutions out of all these least squares adjustment things, because it's an iterative process, and more or less the whole geodetic community is involved. Yeah? You have the observers at the stations which do the observations. The observations are then sent to so-called analysis centers, which pre-analyze the observations, do outlier screening, and so on and so on. Then they compute a solution or a normal equation, send this to the technique-specific combination centers. There they are pre-combined within one technique, and then these solutions are sent to us and the other 2 institutions, and we combine them at the intra or intertechnic level. So we combine really the techniques. And at the end, you get one set of station coordinates and velocities. But there are really thousands of people involved, and it's really a task of the whole geodetic community. Last realization is the ITRF 2014. Currently, we are in preparation for the next realization, which is the ITRF 2020. So this reference frame will include data up to December next year. Yeah. So 2020 is still included. So we will finalize the computations in 2021, and then in summer 2021, so in 1.5 years roughly, the solution is then presented or published to the community. Excuses. Does anybody know what a geodetic datum is? We heard a little bit about this before, but are you familiar with the datum definition? If not, no?
I think it's kind of a location specification when you say how the longitude method, so where on the Earth is it divided in, also in minutes and seconds, to be more specific, where on the Earth is.
Yeah.
Maybe.
Yeah, partly true, yeah. So the geodetic datum describes the, how do I say this? Describes the things you have to specify in order to realize, or to realize the coordinate system. So somehow you're right with the measurements, but let's have a closer look in 2 different examples. First of all, we have the geodetic datum as a set of parameters that describe the relationship between a particular ellipsoid, for example, and a global geodetic reference system. That was one definition given by Seba quite a long time ago. And beside this parameters of the ellipsoid, the geodetic datum contains information about for a complete datum transformation between 2 Cartesian systems. It sounds complicated, but it's totally easy. This is an example. You have a 2-dimensional Cartesian coordinate system, x-axis, y-axis. You have an origin somewhere, and what you have given, or you have as unknowns here, the coordinates of 3 points A, B, and C. Classical terrestrial surveying problem. So what you do in order to get the coordinates, you measure the distances and angles between these different points. So at the end you get 3 distances and 3 angles, alpha, beta, gamma. And the geodetic datum allows you now to refer the measurements you did to the coordinate system you defined. That's more or less the geodetic datum, because you can place these points anywhere in this 2-dimensional coordinate system, and the measurements and the angles won't change. Yeah? So you have to, in order to get coordinates, you have to define the relation between this local surveying network, for example, and the 2-dimensional coordinate system. So what do you have to define in order to get or be able to derive the coordinates? First of all, you have to define 2 translations. So at least for one point you have to know the coordinates delta x and delta y with respect to the origin O. Yeah? But then, if you have only these coordinates, you see you can still rotate the whole measurement or the local system around the A point. It won't change anything in the distances and angles. So secondly, you have to define at least one orientation. So this is, for example, the direction towards north. And if you have this angle given to one of the distances you measure, you also have the rotation defined. So there's only 1 degree of freedom left, because now you have the point defined, you have the rotation defined, but you can still scale the different distances and the angles won't change. So you also have to define at least the scale. And together with the geodetic datum, so the sum of the geodetic datum and the measurements allows you now to describe the points A, B, and C with respect or relative to the original. Yeah? So in the 2-dimensional case, we have to have 4 datum parameters, 2 translations, 1 orientation, 1 scale, in order to define or relate the system to the coordinates. Great. So we have to do the same now for the geodetic measurements. Geodetic measurements are in fact nothing else than any points anywhere located on the Earth crust. We measure distances with SLR, we measure Doppler counts with DORIS, we measure angles and distances with GNSS. So we have to relate them to the terrestrial reference frame. How can we do this now in this 3-dimensional case? And again, our unknowns, the coordinates of the points A, B, and C with respect to the origin. What we have here is we measured the distances and angles to A, B, and C with respect to some reference point. This would be, for example, terrestrial surveying station, a smart station, which is placed in the middle of an SLR telescope, a VBI telescope, and a GNSS antenna. And what we have to define now are, first of all, 3 translations of this point with respect to the origin O. We have then, in addition, defined 3 rotations around the different axes here in order to align these axes with the reference system. And for sure, we have to define at least 1 scale. So for the 3-dimensional case, we have already 7 datum parameters. And we do not, and for sure, measurements plus geodetic datum then allow us to describe the positions or to get coordinates of the point A with respect to the origin or the reference system. This is the datum. That are the datum definitions which are necessary for the 3-dimensional case. So for the ITREF, for example, the ITREF defines the origin to be in the geocenter. This is the equatorial plane with the rotation axis, and then we have the TCG, geocentric time, as the scale. We have measurements taken somewhere in the Earth crust, and we can relate them to the defined ITRES by fixing 7 datum parameters, but we also have to take into account the time evolution. So for the ITRES realization, also the temporal behavior of the datum must be described, and that's why we need 14 datum parameters in this case, not only the 7 offsets, let's say, at a certain epoch, but also the first derivatives with respect to time of these 7 parameters. Yeah? So the ITREF, the 3-dimensional ITREF, needs 14 datum parameters to be defined in order to relate the measurements to the global reference. global reference system. And how does this look like now for the iTref? We have first of all defined a so-called reference ellipsoid. That's a geodetic reference system 1980 defined, so the GRS 80. And according to the IRS convention, we have these 4 or 5 parameters given there. We have a value GM, the semi-major axis of this ellipsoid. We have a somehow dynamical form factor, which describes together with 1 over f the flattening of the Earth, and we have the nominal mean Earth angular velocity. They somehow are incorporated into the datum definition, and then we have to take care only about 3 different points. First of all, the origin, then the scale, and the orientation. This is now really important because the realization, the reference system relies on measurements. So we have to use measurements in order to realize the theoretically defined datum. Origin was defined to be the center of mass. It's inaccessible for us, so nobody can go there and measure the center of mass. So we have to find some observations we use or we do in geodesy in order to realize this. And the origin is, for example, uniquely realized through satellite laser ranging measurements. That's the point, or the point why we can do this, because the satellites do not care about the motions of the observing stations. They simply orbit the Earth, so they orbit within the gravity field of the Earth. So what they do, due to celestial mechanics, they orbit around the center of mass of the Earth. Yeah? Every satellite is orbiting around the center of mass of the Earth. If you have mass redistributions within the Earth system, the satellite orbit is varying a little bit, but in fact it still always refers to the center of mass. If we measure the satellite orbit using SLR, for example, we can use globally distributed measurements and compute the point the satellite is orbiting around, which means in fact that we can compute the coordinates of the center of mass. In fact, you can do this with every satellite technique, because all the satellites, also the GNSS satellites or the LEO satellites, are orbiting the Earth around the center of mass. But we will learn afterwards that only SLR is used. Leave it as it is, like this. Explanation is following in a couple of slides. The scale is realized as a weighted mean scale of VLBI and SLR. So here, in fact, it's the same. Since SLR is an optical measurement technique, yeah, so we shoot a laser pulse towards the satellite, it's reflected and coming back. It's not delayed by the troposphere. That's why it can be used in order to really accurately define the scale. Same holds not in principle for VLBI, since VLBI is a microwave technique, as GNSS and DORIS. Yeah. But VLBI is observing extragalactic quasars which are really stable in their position, and it's not observing the highly dynamic radio emitters like the GNSS or the DORIS satellites. Also leave it as it is. I will explain this when we come to the satellite techniques, why GNSS and DORIS are not suitable to realize the scale and the origin. And finally, we have the orientation, where we had this NNR condition. No rotation offsets or rates are allowed between 2 different realizations. So this is an NNR condition. We learned before with the NNR condition, we minimize the network rotation, or we minimize the common rotation or common motion of all the stations. But you also have to know what is common to all the stations. Yeah? And that's why we use always the prior solution. So for the iTref 2008, we used the iTref 2015. For the iTref 2014, we used the iTref 2008 and minimized the rotations with respect to this coordinate set. This is a purely mathematical construct, so we can divide the datum definition of the iTref in the so-called physical datum. So the origin and the scale can be physically meaningful realized, whereas the orientation is a pure mathematical constraint. It's a conventional definition. We could also say that we realize the orientation with respect to Munich or with respect to New York. Doesn't matter. It's totally up to us. But somehow, to give a historical reason, it was realized with respect to Greenwich. So that's simply a conventional datum orientation. Yeah, the IGF is based on the combination of the four fundamental geodetic space techniques. So we have, as we had before, VLBI. We have, in case of GNSS, for the IGF 2020, that's new. For the IGF 2014, we only incorporated GPS observations into the solution. For the future, or for the upcoming IGF, we will include, or it will be, the IGS includes GPS, GLONASS, Galileo, Baidu, the Indian navigation system, the Japanese navigation system. So there are a bunch of navigation systems online already, and they all will be incorporated into the new realization. We have SLR and we have DORIS. And all of them, that's also a slide we had before, I think 2 lectures ago, they all provide an observation database of roughly 4 decades. So 40 decades of observations are now used, all put together in one least squares adjustment, and at the end we get one common set of station coordinates and velocities. What are the pros and cons of the different techniques? We heard this a little bit in the last lecture already. So in case of VLBI, the advantage is for sure that VLBI is sensitive to all the Earth orientation parameters we have, since we observe extragalactic quasars from crust-fixed stations, and the EOPs describe the transformation of the rotation between the crust-fix and the inertial frame. We can use VLBI in order to perfectly determine this transformation, which means we can perfectly determine all the Earth orientation parameters. In addition to this, VLBI can be used to estimate the scale with very high accuracy. A clear disadvantage of VLBI, it's more, yeah, exactly. We have only a few observing radio antennas which are not optimally distributed over the world, and that leads directly to degradation of the Earth orientation parameters, since it is really costly to build a telescope, to operate a telescope, to maintain it, and so on and so on. SLR. What is the advantage of SLR? Any idea? What kind of satellites do we use within satellite laser ranging? You saw it on the picture before. So for SLR, for the SLR observations entering the TRF computation, we use spherical satellites, so these cannonball-like satellites which are orbiting the Earth. And for these satellites, the perturbations can be really accurately modeled, and that's why, for example, it is the case that SLR is used for the origin definition and for the origin realization and for the scale realization. The advantage of the SLR, of these SLR satellites, is they are cannonball satellites. You do not have to know anything about the satellite attitude of the satellite. Yeah? The satellite does not have any solar panels. There are no active thrusters or magnetic talkers on board. That's simply a solid cannonball with reflectors mounted on board. So it's a passive satellite, and it is orbiting the Earth at heights, let's say 6,000 kilometers, 20,000 kilometers. So you do not have thermospheric drag there. So you can really accurately determine the orbit, which means you can really accurately compute the center or the origin they are orbiting around, which is in fact the center of mass.
If there are multiple reflectors,
yeah,
is it possible to distinguish laser measurements accurate enough to distinguish between the different reflectors?
Yeah, that's a long answer I have to give there. In principle, you are totally right. You can imagine if you have a satellite. If you have a satellite, which is a cannonball, like this, and then you have a reflector here, like this, and you have somewhere here, you have your SLR station. Yeah, this is fixed to then you shoot a laser pulse towards the satellite. It's reflected not only by this reflector, but also by this one, this one, this one, and this one. And what you get back is, for example, back. And at the station, you have a so-called detector, which is single photon or multi-photon detector, and what you get back is such a reflection or such a target signature, which depends on the distribution of the mirrors on board of the satellites. And now you have to distinguish, or you also have to take into account the wavelengths, for example. Are you shooting with green light, so 532 nanometer, or infrared, or whatever? The shape of this reflection function or target signature will change. You also have to take into account the repetition rate. Are you shooting with kilohertz lasers, so more than 1000 shoots per shot per second, or only with hertz lasers? That all influences the signal travel time, which means the range measurement. Yeah? But there are algorithms, and you have corrections computed on ground, calibrated on ground, in order to take into account. But in principle, it's possible. It's even possible to identify the different mirrors on board the satellite with the really high resolution data. Yeah. So, but this is the clear advantage. The attitude modeling or the orbit modeling of the satellite is really easy with these cannonball satellites. Disadvantage is for VLBI that are really costly telescopes. Therefore, they are really inhomogeneously distributed all over the world. GNSS. So now we have the other two satellite techniques. The advantage of GNSS is that we have a really large number of antennas which do a large number of observations. This leads to a very high formal accuracy of the adjusted parameters. A GNSS antenna is quite cheap. Yeah, a geodetic antenna costs like a couple of thousand euros, but then you have a GNSS antenna which can do multiple navigation systems like GNSS, GLONASS, BeiDou, ZSS, and so on, and has a pointing accuracy with around 1 millimeter. The disadvantage is that the modeling of the perturbations of the satellites is really complicated, since the satellite have such a complex shape. They are really heavy, they have large solar panels which are then influenced by solar radiation, for example, and that's why this satellite is not used for the origin realization, for example, because we cannot do this accurately enough currently. Yeah, so the models for the satellite are not good enough, and that's why if you estimate an origin, or if you determine the point where the satellites are orbiting around, you have large variations in this point. You have signatures of the satellites within this time series, and that's why this information is not used for the realization of the TRF origin. The same holds for DORIS. The pro is that we have a large number of ground beacons which are homogeneously distributed over the world. This is a really good or large advantage of DORIS, since this is a passive technique on ground. Yeah? Because in contrast to the other observation techniques, at the ground station the signal is emitted, and at the satellite it is recorded or received. So what you only need at the ground is a DORIS beacon which emits a frequency. So you need a power supply, and that's it more or less. So if you place a solar panel next to it, you can put this anywhere on the globe. You do not have to maintain it. You do, to a certain extent you have to maintain it, but you do not have to operate it manually. You do not have to have an internet connection. And that's, for example, a surprising point, that the internet connection is one of the major limiting factors nowadays. That you cannot place your stations in the Central African region, for example, because you simply do not have the connections to get the data out of this region. The disadvantage of DORIS is that the measurements are less accurate compared to the other space geodetic techniques. This is only due to the nature of the observation due to the Doppler counts. Doppler counts are microwave-based technique. So you have tropospheric delays here affecting Doppler measurements and so on and so on. So this is the only disadvantage of the Doris technique. Okay, what does the combination of the techniques mean? The adjustment of various geodetic parameters is based on the different observations. We put them into a least squares adjustment and get out the combination. And within the combination, the strengths of each technique are used for the determination of the parameters, and the weaknesses are compensated somehow, which leads to a higher redundancy of the estimate. A good example is the origin realization. With a GNSS only solution, you cannot realize the origin properly. That's why you can, in combination, take advantage of the SLR technique, where the origin can be realized really accurately. And in the combined solution, then you have both measurements or both techniques with a good datum or with a good origin information. At DGFI-TUM, the combination approach is based on the combination of so-called normal equations of the Gauss-Markov model. Now, the question is, are you familiar with the Gauss-Markov or the least squares adjustment process? Because I talked about this a couple of times already. So for the geodetic students, it's really boring because they heard this for several times now. Should we go through the slides? I prepared a small example only in order to, let's say, get the basic idea with you. So that won't be the content of the exam, let's say, so you don't have to do the least squares adjustment, but only to see what we are talking about, what are the different levels, and what are the advantages. First of all, there's something before. Okay, that's the realization of DGFI. It's called the DGFI terrestrial reference frame, the D2F 2014. And the D2F 2014 includes now the following parameters. So what do we estimate in our solution? We estimate, as we heard many times before, station coordinates and velocities. And in addition, we estimate the full set of EOPs. And due to the combination, different techniques contribute to the different parameters. So what you see here in this table are the different techniques. Then you have different parameters. And at the very end, you also have the 3 datum categories, or the 7 datum parameters we have to realize. So for sure, all the techniques can contribute to station coordinates, because you have a reference point for each of the instruments, so you can use these observations in order to determine station coordinate. That are the EOPs here, and you see, for example, we learned that VLBI can contribute to all the EOPs, and that's exactly what you see here. VLBI is contributing to all the EOPs, whereas, for example, the terrestrial pole coordinate offsets, so the disalignment of the rotation axis and the set axis of the TRF are all the techniques are able to determine this. LOD can be only determined by SLR, GNSS, and VLBI, and so on and so on. For the origin, we learned that SLR is the only technique to realize the origin. The scale is a weighted mean of SLR and VLBI, and the orientation is then here realized by GNSS. This is a special setup in the DGFI solution, because we have the GNSS network, which is a really dense global network. We minimize the rotations of this network using this non-net rotation condition. So we do not use the inhomogeneously distributed SLR VLBI network. We use this really dense GNSS network and minimize the rotations of these station coordinates with respect to the pre-computed ITRF diagram 2008. Okay, that are the different levels, but maybe we come back to this later. So let's go to the Gauss-Markov model. What is the Gauss-Markov model? This model was developed by Gauss and then Markov. It was extended by Markov. And we can start with a simple problem. What we want to do is we want to fit a linear slope through a set of given coordinates. So what we estimate, or this is the same as we would do by estimating station velocity. So what you have is a time series of coordinates, of station coordinates. In this case, 4 different observations. So you have 4 different coordinates, one-dimensional coordinates at different epochs t. Yeah? So it's a really simple problem what we have. We have 4 observations here. 1, 2, then 2, 1, 3, 4, and 4, 3. And what we want to estimate is, that's our unknown. We want to estimate a station position, or a point here, a coordinate at the time t0, and we want to estimate the velocity, so the slope based on the observations we have here. This means we can define our functional model like this. We have b plus v is equal to this functional model, which is the position at the epoch t equal to 0 plus t times the time derivative, so the slope of the slope of this line, of this linear fit here. What are b and v? B is the vector of observations. Yeah, so there we have the observations. So the y values. So 2, 1, 3, and 4 are in the b vector. In the v vector, we have the vector of the corrections to the observations and the functional model. So the discrepancy, the difference between the blue line and the red crosses. And this here at the top gives us our vector of unknowns abbreviated with x, where we have the offset, the one-dimensional offset, and the slope of the linear fit we wanted to do. Yeah? Everything clear so far? It's really an easy example, but it will somehow hopefully help to get familiar with the mathematical. So we have the vector of unknowns that are our station coordinates and the velocities we want to estimate, for example, for the ITRF, yeah? The GNSS coordinate and its velocity, and so on and so on. We have the observations, which are our SLR observations, VLBI, GNSS or DORIS observations, and we have the vector of corrections, which are then the discrepancy between the theoretical model, the functional model, and the observations. We have special points, or we have also special points. We have to take care about special points in the least squares adjustment. For example, if this point here, epsilon equal epsilon at the time 4 changes to 1. So if this is, for example, not 3 but 1, yeah, the linear slope would change from a positive value to a negative value, so to a totally different value. And that means that this point is called fulcrum, which is a really important point within the estimation. If this point is changing, the whole solution, or the vector of unknowns you estimate, is changing. Mostly they are located at the edges of the time series, but also outliers are can be fulcrums, and that's why it's so extensive, for example, to compute an ITRF, because we have to do a really, really good outlier screening before we estimate our station coordinates and velocities. We will face this, maybe not this lecture, but the next lecture, where we also talk about time series effects. So if you have special effects, if you have earthquakes, which somehow affect your time series, then it's really hard to estimate a good or reliable station velocity out of this. So this is outliers and so on, or time series analysis are a really important point before we do this. So at this point we have no outliers at all. We have these four points, want to estimate, offset, and velocity. So what we do, we can look at the redundancy R, which indicates the so-called degree of freedom of the least squares adjustment. The redundancy is the number of observation minus the number of unknowns. How many observations do we have? In total 4. How many unknowns do we have? 2. Offset and slope, which means we have a redundancy of 2. Usually the number of observations is by far larger than the number of unknowns, which means that the impact of one single observation or observation error on the estimates is minimized. Yeah? So if you have a redundancy of 10,000, then you can imagine that one outlier is not affecting your estimates so much than having a redundancy of only 2. So this is a really, really small one. in the ITF, usually we have millions of observations and only estimate, I don't know, 8,000 parameters or so, no, 20,000 parameters, but you see the redundancies by far larger than here. In this case, we have a more or less linear relationship between the observations and estimates, since we have only 4 observations and two estimates. Usually this is a nonlinear relationship, which means that we have to linearize our functional model in order to get to this linear relationship. So what does this mean? We have our functional model from before, and now we do a Taylor series expansion, and if the a priori values in this case, so your values you set before you estimate anything, are of sufficient accuracy, then the Taylor series expansion could be terminated after the first order correction term delta x. If we move on now, we have here our observation equations. We have the 4 y values, t equal to 1, 2, 3, 4, which are these values now, and they fit our functional model like this. Yeah? So y at the epoch 1 is equal to 2 is equal to the y at the epoch 0, which we want to estimate. So here are our unknowns again, plus 1 times the slope. And for these 4 observation equations, this value is always the same, and the slope is always the same. What do? We construct an equation system here. This is now our vector v again, the observations. Then we have our vector v here. Then we have our design matrix A, which is more or less the matrix of the partial derivatives we defined before, the Taylor series expansion coefficients. So the partial derivative of this first equation with respect to the first parameter is 1. Yeah? The partial derivative of the first equation with respect to the y dot value here is again 1. For the next one, this is 1 and this is 2. This is 1 and this is 3 for the partial derivative. So you get this matrix. Then you have your vector of unknowns, the offset and the slope. And if you realign this now, or rearrange this equation and solve it for v, then you end up with this one. So v is equal to a times x minus the observations. Yeah? If we now move on, we have also a stochastic model where the accuracies of the different, or the standard deviations of the different measurements are taken into account. So you can take them into account. Not so important here, because in our case we only deal with uncorrelated observations with standard deviations equal to 1. So we end up here with the utility matrix 0 and all the off diagonals and 1 at the main diagonal. Not so important, but now it's getting straightforward, because the least square adjustment means that the main goal of this adjustment algorithm is that we minimize the weighted square sum of the observation errors. Observation errors had been the v vector. Yeah? So what we want to minimize is the square sum here. This v transpose pv should be a minimum. How can we estimate such a minimum? We do the partial, or we do a partial derivative of this and then insert the v from before this equation. We can insert into the equation and then reformulate it, and at the end we get this one here. This expression, and this function has a minimum when the first derivative is 0, so the computation of the first derivative is done component-wise, and what you end up is this equation here. It's the left-hand side is the normal equation, and the right-hand side is called the right-hand side. Not so important. You can try to follow this at home. Getting back to the numbers, we have now the quantities A transpose A. When we insert the quantities of the observation equations, we end up with these numbers. If we invert this normal equation, we end up with these numbers. A transpose B would be this. So, and this leads to our estimates. Our unknowns are now the vector of unknowns given here, since we can compute it like this here, is 1 and 0.6. And coming back now to our example, you see that fits quite well. We have epsilon y0, which is equal to 1, and then y dot is equal to 0.6. Yeah? This is now the outcome of our least squares adjustment. Again, here we now see the vector of the corrections, so the difference between the functional model and the observations. You see it's minus 0.4, 1.2, minus 1.2, and 0.4. And if you look at this slope, you see, okay, this fits quite well. 2 minus 0.4 will give you something at this linear slope. We have the next one, which is plus 1.2, which gives this point. So you have here really the discrepancies of the observations with respect to the functional model. We also can compute a standard deviation for the offset and the slope. Yeah, and we can also compute then a correlation coefficient of the offset and the slope. And in this case, it's minus 0.9, which means that the offset and the slope are correlated really high, which means, or correlated reciprocal because it's negative, which means is if epsilon 0 is getting, or y0 is getting larger, yeah, the slope is decreasing and vice versa. They are anti-correlated or correlated reciprocal in this case. And if somebody uses the estimates in a combination, the combination is done at the solution rate. Which means, in fact, if you get station coordinates and velocities from the different analysis centers and combine them, you combine this at the solution level. If you get these quantities here, for example, from the different analysis centers, then you combine it with normal equation. So important take-home message is you have observations, a couple of observations, you have a vector of unknowns, and you can estimate these unknowns by minimizing the differences between the functional model, which is a functional model you have to define, a formula which you have to define, and the observations. Yeah? So this solution here, 1 and 0.6 give you the values for your functional model where the vector of corrections is minimal. Yeah? So which means that your functional model fits these observations the best it can do. Any error you do in your functional model, for example, will lead to false results. So you have to be really sure that your functional model is adequate or physically meaningful in order to get reliable estimates at the end. Okay, this was the excursus to the least squares adjustment. At least you know now how the formal procedure is. If you look it up at home, important is you have observation equations, functional model, and the vector of corrections is minimized. How is the IGRF now computed? So this is now an important slide because it's most probably also the last slide of today, because it summarizes what we are doing at DGFI. So the whole procedure of our 1-year computation is summarized at this this slide. First of all, we get SINEX files from the different technique-specific combination centers, and we reconstruct constraint-free normal equations. Nobody knows what this means. SINEX file. SINEX is an abbreviation for solution-independent exchange format, which means that it's a predefined format used by the geodetic community in order to exchange data. Yeah, so it's a really strict format, and you can exchange technique-independent data sets, more or less. And what we do is we get this data, and we do some pre-processing in order to remove all the data information these data sets have. So we remove the information for the origin, we remove the information for the orientation and for the scale, and what we will get then is a really network of measurements, for SLR, for example, which has no geodetic datum at all. So you cannot estimate coordinates out of this. You have to do something with this. And what we do is, so after the reconstruction, we have a time series of data-free single technique normal equations. So we have our 4 techniques. They are totally independent from each other. And for VLBI, we have, for example, daily normal equations. For SLR and DORIS, we have weekly normal equations. And for GNSS, we also have daily normal equations. So we have to deal with different techniques, with different temporal resolutions, and so on and so on. What we then do is we solve these different technique-specific normal equations and get a coordinate time series for each coordinate. So for each point on Earth, we get a coordinate time series. And then we analyze these time series, so we correct for some uncorrected geophysical phenomena, which are called here non-tidal atmospheric loading or non-tidal current water storage loading. Not so important, but we remove geophysical information. Afterwards, we identify discontinuities, we detect outliers and remove them, and we set up station velocities. Yeah? And this is really important now. If you have a time series, so what we have, like in our two-dimensional example before, we have the time on the x-axis, and here we have, for example, the x-coordinates of our station time series, and we get something like this. Outliers. This is something we get from the technique-specific centers. And in our pre-processing, what we first do is we identify outliers and remove them. Yeah? So everything which is not fitting the regular behavior of the time series is removed. Afterwards, we identify discontinuities in station time series. What is a discontinuity? A discontinuity is then, for example, something like this, when the time series at a certain epoch ti makes a jump. This jump can be millimeters, centimeter, can be meters, and is caused most probably by instrumental changes or earthquakes. So if you have earthquakes somewhere on the Earth, your station can really perform a large jump. We will end up with an example most probably next lecture. For example, within the Chile earthquake, or due to the Chile earthquake in 2010, Concepcion GNSS antenna jumped by 3 meters and 10 within one measurement epoch. And now it's really important, because why do we do this? Why do we identify discontinuities and remove outliers? Because we want to set up station velocities. Because our final product then, the D2F, comprises station coordinates and velocities. You can imagine if you have this time series, for example, you remove the outlier, the velocity you estimate, if you do not take the station discontinuity into account, you would end up with a velocity, something, or linear regression like we had it before, something like this. Or, so this would be your estimate for the velocity if you do not include the station discontinuity. Different colors. Okay. So you now identify this point, and identification means that we somehow try to find this epoch ti. We split up the time series and say this segment is a totally different one than this one, and then we estimate a velocity for this one, and then the next segment like this. Yeah? And then we say, okay, for our first segment, we estimate this velocity, which is only valid from I-1 with I, and then this next is from, the next segment is then valid only from Ti plus until Ti plus 1. And this is a really important step, as you see, because depending on your outlier, you can end up with totally different velocities. Yeah? And that's really important. What you also see in this drawing here is that due to earthquakes, your velocity can change. In the first segment before the earthquake, for example, we have a more or less really flat velocity, which means that in x direction the station was not moving that much, but maybe due to local deformations or post-seismic deformations, after the earthquake your velocity is totally different compared to the one before. So this is really important step, removing outliers and identifying this discontinuities in order to get reliable velocities. And this whole procedure is called the intratechnic combination because what is done then, after we identify this, set up station velocities, we accumulate all the different normal equations of one technique and get one large normal equations out of this. This is the same as we had it before with the different observations of in the excursus. You can say you can say that, for example, for VLBI, a daily normal equation contains one observation for each station. Yeah? It's a daily average observation then for the station Netzel, for example. So what does the accumulation mean is that we sum up all the observations for this station and then fit one velocity through all the different observations. That is done in the so-called intratechnic combination. Intratechnic because we sum up all the observations of one technique. And we end up then with a technique-specific normal equation. And that brings us then to the point that after the accumulation, one normal equation per technique is obtained. So from these thousands of daily normal equations for VLBI, after all this time series analysis and preprocessing, we end up with one normal equation which comprises all the coordinates of the VLBI network and the velocities. And then the same holds for the other techniques. And then there's a second step which is called the intertechnic combination. So intratechnic now. And within this we introduce the local ties, we combine the station velocities, we realize the geodetic datum, estimate variance factors between the different techniques, and so we add them up, and what we then obtain is one solution, the global terrestrial reference frame, D2F, and the Earth orientation parameters. So this is really important. Combination approach at DGFI, we combine normal equations, so this A transpose A matrix, and our combination procedure is mainly based on two different steps. The intratechnic combination, where this here is really important, and the intertechnic combination, where then everything is put together, datum is added, and we obtain the solution. Is this now clear that the velocities and the discontinuities? Because this is really, really important step. And you can imagine, maybe one slide would be really good now. Here we have the collocations. Okay. So we have collocations, so we add local ties to the equation system. We learned already local ties are the terrestrially measured difference vectors between the different instruments. Up to now, only 5 stations jointly operate all 4 geodetic techniques. Metsahobi, Finland, Hartwig, South America, Africa, Washington in North America, Yaldabaoth in Australia, and Netzel in Germany. Maybe I skip this because I want to end up with one nice thing because we discussed this. Okay. Rearrange it a little bit. Because what I want to show you is in the framework of the discontinuities. So we have to identify the different discontinuities. Now let's have a look on the numbers of the D2F. So what are we doing? We have in total 167 million observations. The majority are VLBI and GNSS observations, and then we have a little amount of SNR and DORS observations. So this is our N. Yeah? The redundancy, as in the example before, redundancy is N minus U, number of observations minus number of unknowns. So we have roughly 170 million observations. You can expect this was in 2014. Now we have more than GNSS included in the combination. Galileo, GLONASS, BeiDou, and so on. We have 6 years more of data for the ITF 2020. So we will easily hit the 200 million, maybe 250 million observations for the new realization. Then we have the number of sites, that are the number of coordinates or station coordinates we estimate. That are for GNSS 1,353, and and for the others roughly 100, and for Doris 150. Times 6, because that are the number of sides, and for each side you estimate 3 coordinates and 3 velocities, in x, y, and z dimension. That these number of sides are aligned with these number of unknowns. So you see, for the vast majority of GNSS sites, you have at least one discontinuity or even more in your time series. And also for the others, you have roughly about 50 discontinuities. And now you can imagine what a kind of really expensive analysis this is in order to go through all the time series and identify these 1,500 discontinuities. Why is the GNSS technique having so many discontinuities? Any idea? Because if an earthquake happens, all the techniques are affected. 2 reasons. First of all, as we had as an advantage, we have much more GNSS sites than for the other techniques, since it's really an inexpensive instrument. So we have at least a number of 10 or 1 order of magnitude more GNSS sites than any other techniques. But the GNSS technique is also very accurate. If you look at the time series, you have a scatter of roughly a couple of millimeters in the time series, and you see everything there. If the firmware is updated, if the receiver is changed, if the antenna is changed, if a different cable is used, you see really anything in these time series. And that's why it's really hard, or that's one of the disadvantages of GNSS, that really every technique-specific effect can be seen or can be allocated as a discontinuity in the time series. And this brings us to the final number, the number of unknowns. So we estimate roughly 80,000 unknowns, but only 1/4 of these unknowns are the station coordinates and velocities. The 3/4 are the EOP. And the EOPs are that much because you can imagine you have 40 years of data, and you have each day you have 5 EOP. Yeah, and that they are estimated with a daily resolution. So 40 times 365 times 5 is the number of unknowns for the EOP you estimate within the equation system. This normal equation has now roughly a size of 50 gigabytes. So for the i2F28, we used the Linux and the LRZ supercomputer in Garching in order to invert this normal equation. For the i2F2014, we did this at our home institute, since the computers development was so good. Easily, the next normal equation will be around 100 gigabytes and to be inverted. And it lasts around 2 days from inversion. So you see that how costly this is to be estimated. Okay. Then let's finish here.